The Frame Rate of Video Games by Grabthar's Hammer. What a topic. One day I'll make a video about it. Meanwhile, we examined Ghosts and Goblins and its 20 FPS-ish gameplay in a previous entry in the Behind the Code series, and an effort was made to explain the work necessary for a 60 FPS conversion. We learned that 1/20th of a second was allocated for creating each new game frame, and that time period wasn't without its own set of unintentional subframes that are output to the television as the next game frame is computed. In fact, we saw one instance of a newly scrolled background paired with an outdated set of sprites. It took another frame's worth of time to correct this problem and output the desired pairing of the two. Unfortunately, this meant that wrong frames appeared in between the proper frames of the game. This led to what gamers call jank. One solution to this problem would be to hold all graphical updates until the last moment. While this would work, it comes with a new set of problems thanks to the design of the Sprite engine. So now what? Maybe the best solution would be to just start optimizing code for a higher frame rate at some point in time. Well, that time is now. Hello everyone and welcome to Displaced Gamers. My name is Chris and this is Talkin Code Episode 6, Micronics Sprite Pain. On a personal note, this is an interesting challenge. How do you turn a code review and code optimization into something that is fun to watch? I don't know. We'll find out. When we broke down the various operations executed when building sprites, we also illustrated those code sections using boxes. The boxes represented the execution start time of specific instructions. So as the PPU is drawing the graphics we see for the current video frame, the CPU executes instructions related to creating the next game frame. Our new goal is to jump into the code for these sections and alter said code to accomplish the same tasks in a shorter period of time. When Mega Man 3 or The Legend of Zelda slows down, people might say it is too much for the NES to handle. Well, what is it? It isn't the number of objects on the screen, but rather the CPU time required in cycles to process the next game frame. Naturally, having more objects requires more CPU time, but it is possible that optimizing an unrelated area of code may improve performance, maybe even remove slowdown for the games that have it. Using these boxes on top of frame time is the best way to illustrate progress made as we change the code. The pink boxes represent a period when the CPU is wasting time after completing work for the next game frame. As we reduce the time occupied by the various game frame tasks, the wasting time area will increase in size. That's a good thing. It means more time is available for the CPU to do additional work when we reach a more demanding game area. Alright, now I have two self-imposed rules for these changes. Number one, make code changes that are compatible with making a video. Maybe we don't select the best code to modify or write the best code to replace it, but the changes are easy to follow. Number two, stay within the confines of the ROM bank. Whatever bytes we have available in the bank are the bytes we can change for the code. No larger ROMs, new mappers, or anything of that nature. So let's go. The first section we'll examine is the big one, the code that writes sprite data to RAM. Eventually, we copy the sprites from RAM to the graphics processor. Meanwhile, here's the code. If assembly code is your sort of thing, pause the video and review it. Note that reversal of this area is incomplete. Now that you've seen the whole thing, let's cut it down a bit more for our exercise. I understand if this still looks overwhelming. Fortunately, we don't care about understanding sprite generation functionality so much as finding assembly code we can tweak for performance. Code candidates shouldn't be difficult to find. This entire area loops through each object we need to create, and each object has a loop that creates every single sprite for said object. With that necessary evil of a double loop in mind, you'll notice that many of the addresses referenced in the code contain parentheses. These are pointers. Their values point to a 16-bit address we need to reference for reading a byte or writing a byte, for example. They aren't the most efficient things to use, but they provide flexibility. After we use them to access the value at the address to which they point, we need to change that address to move from 9545 to 9546, for example. How do we do that with code? Where does the code go? Good question. We could write it in line with everything else, but Micronics placed it inside of a subroutine. So use the pointer, call the subroutine, increment the pointer's address, and return. Now we are ready for the next time that pointer is needed. Naturally, we have a lot of subroutine calls. This works. It also saves ROM space, however it is very inefficient. Consider that it takes 12 CPU cycles to call a subroutine and return from it. Meanwhile, the code it executes inside that subroutine may need as little as 7 CPU cycles. It takes less CPU time to perform the actual operation than it does to call and return from the subroutine for said operation. Add to that the fact we have to loop through sprites inside a loop for objects means these subroutines are called even more often than the number of times we can count on screen right now. This is what I want to change. I want to eliminate the subroutine calls. It stands to reason that we can gain performance by copying the code from the subroutine and pasting it where the call to that subroutine used to be. Eliminate the 12 CPU cycles we have to burn for calling and returning every single time. This requires even more bytes than we are using now and will therefore make the Sprite engine even larger, but it will help performance. Now, where do we get the bytes we need? I have good news. First of all, even though we are limited to 64 sprites and therefore 256 bytes, this area of code handles going beyond that if needed. That isn't really necessary. More on this oddity later. So let's remove that code. Second, the first subroutine we see is unused, so we can delete it and reclaim those bytes immediately. Finally, eliminating the subroutine we are copying replacement code from will free up some bytes. We can eliminate a subroutine so long as we replace all of the calls to it. After replacing the various calls to these subroutines with the code that was inside of them, we are left with this. All subroutines have been eliminated, save for one. Some calls to this one still exist elsewhere in code, therefore it remains. It is possible we could eliminate those remaining calls, but this is where I stopped. Let's see how we did. This save state is from the starting screen. We don't have much to do in this example, and all of the sprite work represented by boxes fits inside a single screen's worth of time, even before we start making changes. A solid example screen. It is running the original code. And here is the exact same frame after we made modifications. It is running our modified code. Same save state, different code executed. You can see that our subroutine elimination work inside the Sprite build logic resulted in a shorter period of execution for the build routine. Now let's be honest, this entire Sprite building sequence of code should be gutted and rewritten in order to achieve a proper solution. However, notice that a little bit of copy-paste modify seemed to make a noticeable change in performance. More CPU idle time, or more pink boxes, is a good thing. That is optimization. Now what about these other Sprite areas? The code for them is much smaller in size than the Sprite building section. Can we really do much to those to help performance? Yes, and the results are even better than our first batch of changes. A few small changes can make a huge difference. Watch. After creating all sprites for the next game frame, developer Micronics elected to effectively clear all remaining would-be sprite bytes in page 2 of RAM by writing a value of FF to them. This was done using this code loop. This is not a good loop at all in terms of performance, and I think there is a story behind it. We'll do a conversion with commentary for this one. First of all, this section up here copies the 16 bits of where we left off from one pointer address defined here and here to a different pointer address defined here and here. Why? Because the loop uses this subroutine call to increment through the addresses where we write FF. If we left off on address 260 in RAM when writing sprites, we copy that 260 value to this pointer and use the call to this subroutine to increment through the various addresses as we write FF to them. Sound familiar? Incrementing a pointer address by using a subroutine? Remember how I said we left one subroutine intact when we made our modifications to the Sprite build code? Well, here is one of the calls to that one. Might as well use a pointer and a paired subroutine to manage our 16-bit destination address. Wait a second. Why do we need to worry about 16 bits? As in 8 bits here for the number indicating page 2, and another 8 bits here for where we are in page 2. This entire range of bytes holds all the sprites. Everything is in page 2. We don't need to worry about changing this upper byte to page 3 at any point. We don't need 16 bits of flexibility. We only need 8 bits. If that's the case, we don't need this elaborate setup with pointers. So why is it here in the first place? Why code it this way? If you watch the Behind the Code episode on this subject, you know that the game uses both page 2 and page 3 of RAM. Build the sprites in page 2, reverse copy them to page 3, and alternate which page in RAM we use to build the sprites on the screen. That's the method used. It is possible that all of the sprite code, including the loop we are working on right now, was originally designed to be able to build sprites to either page 2 or page 3 of RAM instead of building to page 2 and then copying to page 3 after that. If that's the case, it makes sense that you would need the 16-bit flexibility to write to either page using the same code. That would explain a lot as to why this sprite code seems needlessly complex. It was perhaps originally written as something even larger in terms of scope and got pared down to something that was unoptimized leftovers. So here we are. We're going to design this loop so it always writes to page 2 in RAM. That's going to help a lot. Time to tear this thing up. Since we're going down to 8 bits, we only really need this item here, which we can put into Y. So, load into Y this value here. And we don't need this, or this, or this. This area here is used for the exit condition of the loop. We'll come back to that. Then, it loads the value of FF and saves it in, well, we're no longer using a pointer. So this pointer goes out, and this will become 200 plus Y. This subroutine is no longer used because we are using Y to handle where we are, so let's get rid of the subroutine call. And we need to increment Y as we go through this loop. So I in Y to increment Y. With me so far? Lots of code changed to something that does the same thing. So this is our exit condition for the loop here, these 3 lines. And what we want to do is combine the condition with the logic responsible for looping. Replace that jump, JMP, with something else that is a conditional instruction, such as a branch instruction. So what we want to do is get rid of these 3 lines. This line, and this line. There's not much left. And then down here for the jump replacement, let's see. If we're walking through all the addresses in page 2 and incrementing using Y, Y will eventually roll over to 0. When that happens, we want to drop out of the loop. So, branch if not equal to 0. Keep looping so long as Y isn't 0. And that's our loop. One other thing left is the FF statement we needed to load every single time through the loop. We no longer need to load it every single time, so we can move it to an area before loop execution begins. What a mess. All this is possible because we moved from needing something with 16-bit requirements to something that only needs to worry about 8 bits at a time, the value we hold in Y. Amazing. This difference between working with 8 bits versus 16 bits on an 8-bit processor. Make our edits and here we are. This new loop is pretty good, but it could be better. We're writing FF to every single sprite byte, Y location, tile ID, attributes, and X location for every single unused sprite we wish to disable. Well, you only need to provide a Y location that is out of range to disable a sprite. Put it on an invalid scan line. We might as well skip the bytes we don't need to worry about. So let's increment Y 4 times for each loop to reduce our total writes and our total number of loop iterations. With the exception that we quarter the number of writes to perform in our new version, these loops perform the same task but don't look the same at all. Also, there's a huge bug here. I left it in for fun. Do you know what it is? What if we write a full bank of 64 sprites to page 2 in RAM inside our build routine? We would exit that routine with a value of 00 in the low byte of where we left off. That 0 would be placed into Y. Our loop would start writing FF at the beginning of page 2 and plow through all 64 sprites. That's unfortunate. That means that after using a full set of sprites in the build code, the FF filler code will erase all the sprites in the game, at least for a few frames. So perhaps we should add a check for that and skip all FF fill logic in the event page 2 is full of sprites. That's better. Okay, it seems to test just fine, or at least now it does. Let's see what sort of difference we made in terms of performance. Here are the boxes that include our modified Sprite building code and the original FF loop logic from before our modification, and here is the performance after implementing our new loop logic. I'm happy with that outcome. It saves a very noticeable amount of time. Remember that the fewer sprites you build, the more time you spend writing FF to the remaining bytes in page 2. We have one more sequence worth tackling, copying all sprites from page 2 to page 3 and reversing their order. Let's take a look. Well, the original is rather interesting. It starts at the end of page 2 and copies to the beginning of page 3. It uses a nested loop, or a loop within a loop, to copy one byte at a time for all 64 sprites. That's 256 bytes. Do we need to copy every byte? Yes. Do we need to use a double loop and copy each byte one at a time? No. Let's reduce this operation to a single loop. We know we have to write 4 bytes per sprite no matter what, so why not just do that? Get rid of the inner loop. Y is used to move us backward through page 2. X is used to move us forward through page 3. Since we copy 4 bytes per loop, we decrement Y 4 times and increment X 4 times. When X rolls around to 0, we are done. So our looping condition is similar to our FF fill loop. Branch if X is not equal to 0. Alright, reducing the amount of looping we have to do should help out a lot. Let's check performance. New build code, new FF fill code, old copy code. And now the same build and fill, but with our new copy code. Yeah, this change also made a difference. Let's compare the new version of all 3 sections to the original performance before we made any changes. I think that's a pretty decent improvement overall, don't you? The crazy thing is, we didn't really do much, did we? So think about all the code in Ghosts and Goblins or any other game and just how much optimization was left on the table. Games that have a slowdown may have room for improvement. Games that were dropped to 30, 20, or even 15 FPS may not require those frame rates after all. Now, what about our example from behind the code? What about when our levels scrolled and our sprites did not? Does our code update help with that? Let's watch the frames to find out. Subframe A and subframe B. Background and sprites moved at the same time. It is just a single frame from the game, but I'm happy that these little changes were enough to have this great of an impact on the very example we used in the Behind the Code episode for G&G. Sadly, we still didn't finish all new framework inside 1/60th of a second. So even though the sprites look okay, this frame set still doesn't qualify for 60 FPS. It needs further optimization. I mentioned gutting and rewriting the entire sprite engine. That would be huge indeed, but the smallest change can help as well. Notice that our new copy loop's last statement executes at this moment on subframe A of our example, on scanline 239 at PPU cycle 300. If we return to the loop code, it is possible to tweak it a little bit more. Instead of doing 4 increments of X that take 2 cycles each for a total of 8 cycles per loop, we could instead transfer X to A, add 4 to A, and then transfer A back to X to accomplish the same thing and use 6 cycles per loop. Additions like this require clearing the carry flag, of course, but we could do that outside of the loop. With this code in place, our copy loop's last statement executes at an earlier moment on subframe A, on scanline 238 at PPU cycle 257. We gained more than a single scanline's worth of time with that simple of a change. While it still isn't enough of a gain to move this exact moment of the game to 60 FPS, it is another example of how various bits of optimization can lead to a gain in performance. Eventually, these gains can contribute to a better player experience. You know, frame-by-frame analysis is fun, but what about actual gameplay? How do these changes affect Ghosts and Goblins? Let's find out. The game runs at 20 frames per second. That means it has 3 video frames worth of drawing time to get the logic done to create the next game frame. It doesn't matter how quickly the work was completed, it always allocates 1/20th of a second. If the work was finished during subframe A, we still have to wait before starting work on the next game frame. That said, wherever we actually finish the work is a good indicator of performance behind the scenes. what could the frame rate be at that moment in time? I wrote a script that showcases during which of these 3 subframes the next game frame's logic was completed. Whatever subframe, A, B, or C, was currently being drawn when logic completed will show up at the bottom of this window on the right at the moment it happened. At the top of the gameplay screen, we have a counter for each of the 3 subframe types out of the last 300 completions of what we'll call a triad. If we finished logic while drawing subframe A, that means 60 FPS was a possible frame rate at that moment in time. We finished all game logic for the next frame within 1/60th of a second. Under that is the counter for logic completion inside subframe B. That means 30 FPS is possible. Finally, the last counter is when we finished next frame logic when subframe C is being drawn to the screen. That means that, unfortunately, 20 FPS is required as we took the full allocated time to process one new game frame. We'll use this information to compare the stock ROM's performance to the performance when executing our modified code as the game is running. This first area of the game would appear to support 30 FPS most of the time when executing the original version of the code. The appearance of enemies or any object limits potential performance to 30 FPS. Moving through the 2-level terrain area here even dips down to requiring all 3 frames of a given triad to compute logic for the next game frame. Not many instances, but they happen. Even level 1 can get really busy. If we switch over to our new code, the start of the game actually shows us that 60 FPS is very possible. We only made a few changes, and look at this improvement in performance. The 2-level area demands a lot more work, of course, but we don't require any C subframes, unlike the unmodified version. Completing this battle and proceeding through the level puts us back into the 60 FPS possible zone, and this continued jump up into the green area makes you wonder just how possible 60 FPS would be for all of the first level. I believe this is an indicator that replacing the build area of the Sprite engine with something much more optimized would push us even closer to the possibility of 60 FPS. This is the toughest stretch of the level in terms of computing. A new Sprite engine would help a lot more, and we haven't even talked about potential optimization for other code in the game. If we return to the original code and watch a stretch of level 2, we hit the area with the worst performance for the footage I recorded. This stretch here really drops down into the 20 FPS required zone. In fact, when we move to the right side of this building to work our way down the ladders, 20 FPS dominates the triad results. We are far away from thinking about 60 FPS here, but let's see how our modified version fares. Wow, we still pick up some C frames of course, but look how possible at least 30 FPS would be through this section. Now obviously we would want to check performance for the entire game, but this stretch here may very well be an indicator that at least an increase to 30 FPS is possible for Micronics' entry for Ghosts and Goblins. There you have it. Same graphics, same physics, same enemies, and so on, but different code for the same tasks can make a huge difference. And we didn't change much code at all. The changes we did make would still use the same ROM size and PCB configuration for the original NES game. No new fancy mapper chips or larger ROMs are required. Well, I hope this helps showcase the benefits of code optimization for games of this era. Who knows? Perhaps 60 FPS on Ghosts and Goblins on the NES is closer than we think. Like, comment, and subscribe for more videos like this one. I also have a Patreon available if you are interested, and thanks for watching.